Let me teach you something real quick.
So,
If you have an option, you do not pick multiple choice. My God. Or you just haven't had a teacher that's made a multiple choice test
Like all the answers are
remarkably difficult. Yeah, I mean,
I've taken it in high school.
they suck so bad. I'd rather have somebody looking at the whole damn thing give me partial credit for the parts that I got right, instead of I make one mistake at the end, so I pick 3 instead of -3, and the machine says it's wrong.
But you're kind of harsh on cylinder grading. Seems like
Yeah.
you take chunks of points out for one little mistake. And it's like choose.
The more I take it for 2 reasons. I take a lot of points off. One, if it's conceptual, like you didn't know what you were doing.
Yeah, you already mentioned
And
that.
secondly, if you make a mistake like I had up here a minute ago, especially if you do it a couple times. I mean, that's pretty bad. All right. Are there any leftover questions from chapter 13? I think last time we did 13.5. We talked about the hammer. Remember that?
Yep.
Good. Very good visual, yeah. Say again? The homework, which one? 5? Number 5? 20? Okay. So this is the one like this here? Right?
You mean 22 was what we had to sign.
We can do 20 if you want.
Whatever. That's similar.
That one? So this one, can somebody tell me, looking at what's inside those integrals, what are they trying to figure out here? What will this end up being? Given the fact that there's a 1 in there.
Volume.
Volume, yeah. Cool. And so this could have been set up with a double integral. So this is kind of, remember I tried to explain to you that the lamest way to make a triple integral is to take, what I would normally do is it's really the volume between 4 and square root of x squared plus y squared. Because the very first step, I'm going to get a z in here, I'm going to evaluate between these two, I'm going to get the subtraction of those two. So it's exactly like in Math 180 when I want to find the area between two functions. Or you take the top one minus the bottom one. I could have made any of those a double integral where the top was in the top limit and the bottom was in the bottom limit. So it's kind of, that's what I call a lame example of a use of triple integrals. So the very first step here, you almost don't have to do the work. Because the very first thing you get here is z evaluated between those two things, so I get this here. Now they do ask me to use, I'm going to do that even before I change. They want me to use cylindrical coordinates here, right? So they want me to use cylindrical coordinates. And what are your variables in cylindrical coordinates? Who remembers?
Rho.
Careful, rho is for spherical.
Oh.
So in cylindrical, I still have my normal polar, and then I just add the easiest way to get 3 dimensions is just
R theta.
z. Yeah. So r, theta, z.
Replace the x's with cosine.
Exactly. So I still have x equals r cosine theta. Y equals r sine theta. Z equals z. X squared plus y squared is r squared. I love it. So now just make all your substitutions. But as you're doing that, what does this become? Yeah, r dr d theta. I love it. Because that's still just dA. Don't think dy dx. Let me substitute. No, you think dy dx is dA. And what's dA in cylindrical? Because it's still polar there. It's going to be r dr d theta. Cool. So the rest of this should be not too evil. These, let's figure out what's going to happen here. So I want to change this to dz r dr d theta.
Is that the same thing as like, you know, when you're switching things around? Like, does it have, is that like a primary setup DC or DC?
Yes, exactly, for cylindrical, normally that's the way it is.
But it can like change.
It can. Normally z is could be a function of r and theta, right? And r could be a function of theta, and normally my d theta is on the very outside because it's normally just between two constants, yeah. But I could certainly make an equal problem that's not following that, but no. I won't do that. So I could do this first step, but let me just work with the way they give it to us. First step is really nothing different. But this would become what?
R.
R
Still 4.
4.
to 4.
Negative square root of 16 minus
Or
cosine
it could be
squared.
R squared cosine squared.
Where are we looking?
The middle.
In the middle, yeah, 16 minus x squared would be 16 minus
R squared cosine theta.
r squared cosine squared theta. Right? So that's what would go here and there. And what is this? This is saying that x goes from -4 to 4. So what do we really have here? What do these describe here?
Circle.
Good. And in fact, this is why I like to do this step first, so I can really focus on the part that's hard, because the z's stay the same. Who cares about the z's? So I can do that step first. Now this is going to be a circle, and it's a true circle. Goes -4 to 4, -4 to 4. Because at 0, of course, this is 4 and this is -4. You with me? So as x goes from -4 to 4, y goes from the bottom part of the circle to the top part of the circle. I love it. So what's my last integral going to be from to? It's now got to be related to theta.
0.
I like it. So it's going to be 0 to 2 pi to get all the way around the circle. Negative square root of 16 minus r squared cosine squared. And then finally integral, I'll screw that, let's just do this. 4 minus, this would be r. Oops. Okay, cool. So a cylindrical, the main thing to worry about, the part that's going to be the most difficult to transform, is the dx dy to r dr d theta, right? The r and theta. So give yourself a picture of what's going on. Okay. Yeah.
Isn't that going to come out with an answer with respect to R though?
Well, then you could still integrate r squared.
Oh.
Easy. It's 4r minus r squared.
No. He's meaning once we put those in for r, that's a problem. And that's because I'm being kind of silly on these. I mean, what's r go from to? I don't really need all that.
0 to 4.
0 to 4, yeah.
Oh,
That's better. Sorry. Because I could just see that from the picture there, right? R goes from 0 to 4 all the way around. The theta makes it go all the way around. So I was trying to plug too much in. Yeah.
Does that work for every problem? R.
Yeah. For cylindrical, if they give it to you dz, dy, dx, you could do this first step. Kind of take that integral kind of out of the way. And then focus your attention on drawing this in 2 dimensions, thank God, right? So draw it x, y, and then see how it relates to r and theta. And that was a mistake I made. I was getting too focused on replacing this instead of just stepping back and looking at the picture. It's just a circle, radius is 0 to 4. Not a big deal, right? That's all I had to plug in over there. Cool. Okay.
like if the limits and each, like say that second, like the dy, how, you know, it's kind of complicated. Like,
Yeah, here to here.
yeah, like if they weren't as complicated, you can still solve everything and then plug in the coordinates, like the x equals, or the, you know, r equals to x squared, whatever.
You
Yeah,
could,
yeah,
especially
yeah.
if they gave you more complex stuff here, you could just plug in what x is and what y is, and x squared plus y squared. Here you do have to be careful, as somebody pointed out, just plugging stuff in, you don't want to end up with an r value in there, because then you end up with a variable instead of a constant answer. But in general, actually graphing the region that this describes first, and then just going straight from that region into r and theta. So this region, this describes a circle. So then r from 0 to 4, theta from 0 to 2 pi describes that same circle, that same region. So that's going to be my limits when I change over to r and theta. Maybe. Okay, cool. This is actually the same thing we did, well, we wanted to do on number 5 on the test. Except I wasn't really changing from one system to another, I was just changing the orientation around, right? Instead of going x and then y, I want to go y and then x. But you still do the same thing, you graph it according to what it's given here, and then you look at it the other way. So if I graph this here, I can then forget about this and just describe that using r and theta. Radius from 0 to 4, angle from 0 to 2 pi, bam. Any other questions from homework? I know we just have one section under our belt since the test. Okay.
I guess what I did in the test, how you got the square root of 16 minus r squared. So I made 4 minus r and they multiplied the r. That's how it was 4r minus r squared. And you said, what?
Yes, I did. I really, really did. Because what is the square root of 4 plus 9? It's not 2 plus 3. This is the square root of 13. Because again,
Right.
I can't distribute this. Powers can't distribute across plus. Yeah. So you can't apply the square root across the subtraction.
That's, huh? But,
So see me
okay, if you
afterwards.
didn't change those coordinates, like the 4 minus r, like into r's, but if you kept it the 16 minus x squared minus, I don't know.
Yeah, see me later.
I,
Yeah. Okay. So real quick, before I get too far away from that, just to kind of do one like was on the test. If I would have said this here, yeah, that'll be fine. Root y. Yeah, I don't want to do exactly the one that's on a version, so I took one and modified a little bit. I changed this little bit, changed that a little. So it's a lot like most of everybody's versions. Yeah.
So square root of y, square root of 4. Make it
Y. So a mistake that was made, a few people made the mistake of doing 1 to 9 on the x-axis. But of course, what does by integral say?
Y.
Yeah, this integral goes with dy. So that should be on the y-axis. A few people forgot about this 1. You had 0 sitting in there, and they really can't start at 0. So on the y-axis, it goes from 1 to 9. On the x-axis, it goes from what to what?
-1 to 9.
So -3. So it goes from -3 to negative root y, which would be this basically. And where does it match? Where at the extreme y value? What is this?
9.
Which is -3. So they match up right there. So it would be from here to there. That's how this integral is set up, right? So as y goes from 1 to 9, x goes from -3 to the curve. Here we go. How we doing? So a few people drew something like this, and you maybe had the other side, and you thought it was inside here or something, but it's very prescribed. It tells you exactly what it's allowed to do. It can go from -3 to the negative side of that curve. So it can't possibly go over here. So it's got to be in this little section here. So when I go to turn this around, now I want x on the outside. What does x do? What constants? Yeah, -3 to -1. Because when y is 1, x is -1. So x is going to go from -3 to -1. Now you pick a y. That looks pretty good. And y goes from this to this. And of course y equals what? X squared. Don't put a negative in there. Why does that need a negative? Because that tells you why x squared is not invertible. Because you need a plus or minus when you try to solve for it, right? It's still all part of y equals x squared. It's just this side of it. So don't think you have to throw a negative on there. No, it's y equals x squared. So it goes from 1 to x squared. Okay, so a few of you guys had like zeros here and there or somewhere. You were going a little too far with your region. But I gave I think the graphs themselves were roughly 2 points, and setting this up was the rest of the points for the problem, roughly. Okay, so hopefully that'll help you out. On part C on that problem, just to warn you guys, if you didn't realize this when you first took it, it needs 2 intervals. Right? The graph should look roughly like that. They should meet there. Be very nice right now. There's some point to break up the interval. So the region looks something like that. It's really nifty. There's your log. There's your negative slope line. So somewhere it goes from going from here to the log to here to the line. So that's why you need to break it up right there. Cool. Some of you guys didn't realize that they meet there. So you weren't sure what to do with that part of the interval. But that's a big hint. So 5C, you need a couple of intervals. Okay. So, what do you guys, if you've ever watched the news, anybody still watch the news? You know, I mostly watch just the Daily Show and then read the newspaper. But on the news, whenever they had the weather report, and they were talking about wind gusts, right, or whatever, they'd show you a picture, and sometimes you even see real time the little arrows were swerving around. But you can kind of follow a pattern, like if it was mostly from the southwest, you'd see the arrows all mostly that way. But then maybe there's a curve to them at the end. So you'd see something like the U.S., oh boy, that's great. Maybe not the U.S., this is some state. And you'd see like arrows like that, maybe.
You can kind of like family occur. Like in differentials, they have like.
You're exactly right. I want to. So if you've taken DiffQ, or if you're currently taking DiffQ, I think it's one of the first things you do is you talk about what do they call it there? Not vector fields. They call it derivative fields. Huh?
Like that.
Family of curves. Yeah. That's right. Because they all have to have slopes at certain points, but they're not set. Yeah. Okay. So this is an example of what's called a vector field.
Slope field.
Because what should be true? Why is that arrow larger than this arrow? What would that designate here physically? Yeah, bigger wind, right? Stronger wind there. It's going a faster mile an hour. And this kind of relates to, I think I told you a story about the billboard they used to have, which would tell you the speed and the direction of the wind. So one time it said 0 from the northeast, and I'm like, that's neat. You can tell which direction the wind is facing, just getting ready to move. So, something else that could really, and here's a cool example. We'll actually see an example of what the function could look like that describes this. And these functions are going to be kind of strange. If I remember correctly, this is our first example of a true vector-valued function of a vector variable. That's a mouthful. But what we want these to do, at every point, if I'm talking about the wind, at each point physically out there at a slice of time, what's coming off of that point is its own vector. So somehow this has to define, for every given point, there must be some kind of a vector output. You with me? So if I move over a little bit, maybe the wind is going this way. Move up a little bit, it's going this way. I'm in the middle of a freaking tornado. Right? Okay. So another example would be, this is an exaggerated view of a blood vessel. How do you think blood should flow through that blood vessel? Where would it be flowing the fastest? And where would it be flowing the, yeah. So your vector field should be something like this, possibly, where it's going to 0 at the ends. And this would be same thing true about any river. You know, towards the outside, the water's flowing not at all. It's flowing fastest towards the middle, right? And it might not be a huge variation in speeds through the middle. It might have exaggerated this, but still it's flowing fastest in the middle, slowest in the outsides, minus any obstacles, you know. We talk about obstacles in rivers, and of course obstacles in blood vessels. And those always screw our equations up, the damn things, right? Of course, only math people would be worried about their equations more than their arteries, but that's so somehow, what's true about this? Let me call this the z-axis. So we've taken the whole thing and put it on its side. So this is the z-axis going in. So in some way, this is the x and y-axis this way and coming out. You with me? So what's one attribute of this field? This is called a vector field that you can tell me about. The motion is entirely
Positive.
Yeah, you can say positive, but I'm going to call that the z-axis going that way. It's positive.
Unidirectional?
Entirely.
Yes, because there's no components in the x or y direction, right? Of course, that would be bad if you had some rupture here and suddenly you're getting this kind of thing. That's not good, right? So we want it to all be pretty unidirectional. I like it. So how are we doing so far? This is the, we've seen stuff like this before. We've seen vector fields before. We're going to look at the math behind it. And part of this is actually kind of just makes sense. Who remembers what the gradient tells you? What is a gradient?
Direction of highest.
I like it. So it's the direction of quickest descent. Is it the same everywhere for a given function? No. For every point, it changes. And what is the gradient physically? Is it a line? What is it?
It's a vector.
It's a vector. So the gradient is actually, we just didn't put it like this, but the gradient could have been our first experience with a vector field. Because at every single point, it defines a vector. That vector has physical meaning. It means you go that direction, you're going to climb the quickest, or whatever the output is going to grow the fastest, right? But it's an obvious candidate to make a vector field out of, so that I'm just not looking specifically at some point. I want to get somehow a graph of what it looks like at every point. Cool. So obviously, we're hoping for a lot of 2D stuff to do. But this works in 3D also. We're not going to do a lot in 3D because that's hard enough. You draw an arrow in 3D. Okay, where's that arrow? I have no freaking idea. Is it right here? Is it way down there? I don't know. Right? There's no real good, what am I trying to say? No good point of reference. All right, so enough conceptual stuff, at least visual conceptual. Let's talk about the math. So that's what we're talking about. So the gradient is a beautiful example of a vector field. Because what is the gradient? Let's say of x and y. Let's not do three-dimensional yet. We're not fully 3D. Yeah, so it'd be fx at xy, fy at xy. There you go. So it is a vector field, but we didn't describe it as such because we were only interested in specific points. So we plug those points in and get an actual answer for the gradient at that point. So this chapter will now allow us, or we finally realize, we just draw this by itself. Not for a specific point, just a general representation of what it's doing. Okay. And of course, how should, well, we'll get to that. I'm not too much about that. Oh, so here's let's look at a specific example. And we're going to first start with 2D. Thank God. This seems very simple. It's a little hazardous to start with this example because this could be any function of x and y. This could be any function of x and y. I just choose it to be x and y. Those are my functions. So this is a very simple example of a vector field. So let's get used to how to draw these things. Let's try some inputs. What kind of inputs will we have?
Here, right there.
Yeah, so a good input to start with is, let's say x, y, and this will be f of x, y. So point 0, 0, it comes out with the 0 vector. Cool. So at 0, 0, it's not going anywhere. Just staying right there. Let's do a couple of specific points, and then I'll see if there's a better way to kind of do this kind of problem. What about the point 1, 0? Yeah, how's it come out? Careful now. The answer's got to be a vector.
1, 0.
So 1, 0, that's incredible enough, right? You gotta love this. X, Y, X, Y. The length here is 0. What's the length here?
1.
1. Cool. We can do the point 1, 1. That'd be the vector 1, 1. The length would be
1 square root of 2.
square root of 2. I love it. And so forth. I really don't want to do this forever. I'd rather just kind of do it in general. The interesting things to realize, what kind of inputs would make this interesting? The inputs that are along the x-axis, the inputs that are along the y-axis, the inputs that are along maybe y equals x. So let's look at that first. Along the line y equals x, what do the outputs look like here?
Y, Y, X.
Yeah, x, x, or y, y. So the length would be
X square root of
x squared to 2. I love it.
Right?
So they're going to point the direction x, x, and the length is going to be x root 2. So for example, and we already kind of saw that here, where x is 1, so the length was 1 root 2. So along the line y equals x. It's a very interesting way to do that, John. So like at the point 1, 1, it's going to point the direction of 1, 1. So it's going to point, as if it was here, it's going to point this way. And it's going to have length 1 root 2, which is basically the same as if it was from here to here. It's just been kind of picked up and moved there. You guys got it with me? A little bit? What about at the point 1/2, 1/2, for example? That's still on that line. At the point 1/2, 1/2.
root 2 over 2.
Yeah, it's going to be root 2 over 2, the length. So the point 1/2, 1/2, it's basically going to do that. How are we doing so far? A little bit decent. Okay. So once you start looking at this thing, what about along this way? Same idea, right? Except now for -1, -1, it'll be pointing in the direction -1, -1. It'll have the length. I've got to be a little careful. It should be absolute value because there's square roots involved there. Are you with me? So now that we're going to negative, we go, crap, I need an absolute value there. But it's going to be the same thing, isn't it? At -1, -1 is gonna point this way. You guys with me on that? So, one way to kind of think about this is you've got the vector at -1, -1, but that vector sits where? At the point. So it's been picked up and moved. So you draw it as if you would have drawn it from there. You just draw it starting here and down. So you are drawing that vector -1, -1, just starting at the point -1, -1. How are we doing so far? So this is the first time we've seen this not really meaning it's in standard position. We're actually graphing it where it's supposed to be. Okay, maybe. And so incredibly enough, what's going to happen anywhere I look? I mean, if I look along the y-axis, which is x equal to 0, it's going to look like 0y, right? So on the y-axis, good. So at 1, it's going to be like this. With me? At 1/2, it's going to be there. At 2, it's going to be there. Because at 2, what length is it going to have? 2. How are we doing so far? So you can pretty much, you can see what's going to happen here. It's going to be the same thing down here. At, oops, sorry. At 1/2, it's there. At 1, it's there. At 2, it's there. And I'll bet you anything here, it's going to be the same way. So not surprisingly, we call this a radial vector field. Because all the vectors seem to follow the radius, right? They're all fleeing the center. So it looks like spike spokes, possibly, depending what kind of bike you got. So we call this an example of a radial vector field. Directly away from the center. Okay. So let me let you take a minute. I know this is brand new, but do what you can. Try to investigate this. Let's see, what did I make it? Let me do one thing to it to actually make it easier. You see who amongst you actually realizes this is making this easier. Because now what length do they all have? They all have length 1. I love it. So not too worried about the length of the arrows, really. I'm trying to help you out there by making them unit vectors. Try to figure out what the shape of this would be. Try to do something like we did here, looking along y equals x, y equals -x, along the y-axis, along the x-axis. Figure out what those would look like. You could put a couple of specific points in to kind of get started.
Is that a comma after 2?
Yes. Real quick, for example, what would f of 3, 4 be?
3 or 5?
That would be 5. I agree with you. 4/5, comma,
-3.
-3/5. 3, 4. It would be pointing in the direction of 4, negative 3. So it would be pointing in the direction of 4, negative 3. Very roughly like that. Wouldn't be exactly a 45-degree angle, but I'm just wanting the rough shape of this. You guys see that? How to think about this is pointing in the direction of 4, negative 3. So it's going to be pointing that way, roughly. And it's going to have a length of 1. I'll do a few more representative points if you want to, or look along the axes in y equals x and see if you can figure out what this thing is going to look like. You should start to see a pattern pretty soon. So if you could do a few representative points. Obviously, you could do all the multiples of 3 and 4. Like negative 3, comma 4, 3, comma negative 4. You get something like that in all of the quadrants. Down here, it would be here. Here would be there. Here would be there. And already you should realize what's going on here, right? Possibly. So everything along the x-axis is going to look like this. All along the x-axis is going to look like that. So right here, it's going to be there, there, there. Because it's pointing in the direction 0, negative 1. So it's just pointing straight down. So that's kind of matching up with our whole idea. Maybe this is some kind of a rotation, right? Like the tornado we were talking about earlier. Then you can do the y-axis, and of course that's just going to make it 1, 0. So on the y-axis is going to point that way. I do have to be careful. There's one little thing. This is along the upper y-axis, and the upper and the positive. Because this should really be, when x is 0, what do I really get here? Y over the square root of y squared, 0. And what would this be? Y over the absolute value of y. So that would be plus or minus y, depending on which side you're on. So for negative y's, it's going to point that way. And it's still matching up with the whole idea of some kind of a rotation. And incredibly enough, they call this a rotation field. So if I wouldn't have put that division by the length, they would have what would have been true about the arrows? They get bigger as you get further away from the center. I love it. Cool. So this just keeps them all unit vectors, which is a little less physically accurate about something, possibly. We don't normally have constant velocity and something like that. Okay, cool. So we have a really simple example of a radial vector field. This is a simple example of a rotation vector field. So let's do this, let's talk, oh, you wanna take a break? Let's do that. Let's take a break till about 5 till. And we'll try to finish out 14-1.
I've actually gotta go. I've got an appointment.
Oh yeah, good, that's all right.